Hi, Andre.
Hi, Melissa.
Um,
Um,
so I'll share my screen if it's okay.
yeah, sure. I'll stop sharing mine. Yeah.
Oh,
Melissa. All right. Greetings, everybody. Today I'm very happy for the special lecture introduce Melissa, who is the world's best person to tell us about virtual fundamental classes in numerative geometry. Please, Melissa.
oh, thank you. Yeah, I'm not the best expert, but I will try to explain this. So fortunately, so Andre already gave plenty of motivation in the past 4 months. So the general setup is the following. We have an enumerative problem, and this gives rise to some moduli spaces called curly X. So in all the examples that we have seen, this is a virtually smooth, the Lin-Mumford stack. So it is usually not actually smooth, but just virtually smooth. By virtually smooth, this means it is equipped with a perfect obstruction theory, which I will define more precisely later. But it is an object in the derived category in this Deligne-Mumford stack, and locally it is a two-term complex of vector bundles, and this gives, it is not usually not smooth, so it doesn't have a tangent bundle, but this perfect obstruction theory gives us a virtual tangent bundle, which is locally the difference of two vector bundles. Yeah, so thinking it as some element in K theory is a difference of two vector bundles. And then, so the virtual dimension of this perfect obstruction theory is the rank of this virtual tangent bundle, which is rank E0 minus rank E minus 1. So given such a virtually smooth Deligne-Mumford stack of virtual dimension, let's say D, Baron-Fantacchi construct a virtual fundamental cycle or virtual fundamental class. So it depends both on this Deligne-Mumford stack and the perfect obstruction theory. It is the element in the child group of this virtual dimension. Because it's a stack, so we use rational coefficient. Oh, so in this talk, so all the stacks and variety are defined over the field of complex numbers, and the child group or cohomology groups are over a rational coefficient, unless we say otherwise. So I'll suppress the coefficient ring and just write without the coefficient. So in some cases, the moduli space is actually a scheme. So if X is a scheme and you apply this construction, so the virtual fundamental class you get will actually be in a child group with integral coefficient. You get an integral class. If X is smooth, so it is actually smooth and it has a tangent bundle. In this case, the obstruction theory is like it actually just has one term as 0, which is the cotangent bundle. And this D is the dimension of X. And in this case, this construction will give us the usual fundamental class. So that's why it is called the virtual fundamental class. Also, yes, I think in this series of lectures, there's a lot of quantum case theory. So following Y.P. Lee, so again, given such a virtually smooth Deligne-Mumford stack, this actually gives us a virtual structure sheaf Yeah, which is an element in the derived category of this Dillon-Mumford stack. In particular, if X is smooth. And we take the perfect obstruction theory to just be the cotangent bundle of X, then this virtual structure sheaf is just the structure sheaf of X. So my understanding is like this enumerative invariance in general is you take this. So right now we don't have any assumption on the properness of the Dillon-Mumford stack. But if X is proper, then you can define cohomology or K-theoretic enumerative invariance by push forward to a point in cohomology or K-theory. Sometimes you can also do proper push forward, not over a point if X is proper over some other thing. Okay, so that's the goal. So now the next thing we want to do is just to try to explain what a perfect obstruction theory is and describe how Baron-Fantacchi construct this virtual fundamental class. So would X be a Dillon-Mumford stack, a perfect obstruction theory on X is an object of derived category. Also, by this we mean like if you take the cohomology of this complex, this is 0 unless I is equal to 0 and 1 minus 1. And moreover, we have a morphism to this is the cotangent complex. Yeah, we will describe it more concretely very soon. Cotangent complex. So this is determined by the underlying Dillon-Mumford stack, and this perfect obstruction theory is an extra structure. So we require that H0 yeah, let me just write this way. H0 is an isomorphism and H inverse H minus 1, sorry, phi is a surjection. Okay, so now we want to understand an object on a stack by taking a cover, an atlas by schemes, so that we can understand in terms of schemes. So recall that if X is a scheme, you can have an atlas where each U alpha is an affine scheme, like spec of some ring, and then this is a disjoint union, and this is an open embedding. So if we have a scheme and we have any object, we can restrict to an affine chart and understand it in terms of commutative algebra. So now if you have so now if X is the Riemann stack or an Artin stack, so you can have an atlas. So in the Riemann stack case, where each U alpha is an affine scheme, and U alpha 2x, so this is eta. And in the Artin stack case, this is smooth. Okay, one second, please. So now let's consider. So we are going to describe this. Consider the following. So we have an affine scheme and an etomorphism. So on X we have phi this. So then we can pull this back and we get phi u and EU and LU, and we want to describe. So then this is all on some affine scheme, and we want to describe this. So consider I, which is an close embedding to something like W, which is actually a smooth non-singular scheme. So then we have ideal sheaf of so now in like just photon the intersection theory, we have so this is classical. We have normal cone of the embedding, which is and also normal sheaf of U in M. So now there's a like surjection from the seam to this direct sum. So we have actually so then on this, so actually in the construction we only need to use the like truncation, the 0 and -1 part of the cotangent complex. So we have So the first two term, like on U, is if we have a close embedding of a non-singular scheme. So this term is the restriction of the cotangent bundle of W. And this is the conormal. And now we may assume that we can actually choose, so this locally, we can choose, this will be vector bundles, and we can assume this is isomorphism, this is surjection. And then we can apply the spec, and then what we will get is so this is the total, this is the dual of this vector bundle, and then we identify with this. So we have so all the condition of a perfect obstruction theory, like this surjection, isomorphic or surjection, so this translates to the following. So we have the following close embedding over U. So this E1U is just the dual of this E minus 1U in the perfect obstruction theory on U. So this is a vector bundle. Let's say it's of some rank D1 over U. And this is an abelian cone over U. So the fibers are vector spaces, but it might have different dimensions at different points. And then this intrinsic normal cone, it's just a cone over U. And moreover, because we have, so dually we have some map from, let us actually identify this with, so there's an action, and then we actually can, so this, the pullback of the, so I take the dual, so the restriction of the tangent bundle of this non-singular W, it acts on this cones. So let's take quotient. So we get some close embedding, but now they are stacks. They are cone stacks over this affine scheme. So notation, so we write this as like underline U, and this is, so this is now becomes a vector bundle stack over U. So each fiber is like the quotient of a vector space by the action of another vector space. This is, in the middle, we get abelian cone stack. over U. And on the left, we get cone stack over U. So C underline U is called intrinsic normal cone, because after you quotient this, it doesn't depend on the close embedding. It doesn't depend on the choice of W and the close embedding I. It's actually intrinsic, and it's pure dimension 0. So this has pure dimension equal to the dimension of W, and then so it acts on, so you get a cone over U, and then it quotient by the action of the restriction of the tangent bundle of W is a vector bundle of whose rank is equal to dimension W. So after you quotient this you get this intrinsic normal cone, which has, you can be very singular, but it has pure dimension 0. And then these are all close embedding of cone stacks over U. So these are like intrinsic, and also we have this. So now, actually, so this actually all glue together to form some like global object on our the Lehmann-Mumford stack. But locally on the affine charts, it's just explicit as this is. So this is the intrinsic. Oh, yeah, let me so these are close embeddings of cone stacks over our the Lehmann-Mumford stack X. This is the known as the intrinsic normal cone. Yeah, it's a cone stack over X. And this is the intrinsic normal sheaf. It's a abelian cone stack over X. And finally, we have this. So these two things are determined by X itself, whereas this vector bundle stack, so this is some vector bundle stack of what rank? So it's of rank D is equal to the so this is equal to negative of the virtual dimension. So now let's look at this. So we have a vector bundle stack over a Dillon-Mumford stack. But let's consider a like more classical setup in Fulton's intersection theory, where you have just a vector bundle over a scheme, and the scheme can be singular. Say this is a vector bundle of rank R, and we have Ginson map. So this is like intersecting with the zero section. It's then okay. So we are on scheme. So child group with integral coefficient. So given an element in the this child group on the total space, so this Ginson map gives you a class degree D minus R class in the base in the zero section. So crush. So now the case we have is actually the following. So the base is now a Dillon-Mumford stack, and yeah, I don't actually need this pi. This is a vector bundle stack of rank R. Then in this setting, one also has a Ginson map. Now with a child group with rational coefficient from this Artin stack curly E to the child group of the base. Okay, so once we have this, so what is the virtual fundamental class is defined to be the following. So you apply this to like recall that we have seen that the intrinsic normal cone of X, so this closed embedding, so this has pure dimension 0. It defines an element in the zeros child group of this vector bundle stack. So now this has rank minus the virtual dimension. We get okay, so this is the construction, but again, we would like to understand this Ginson map on this like for this vector bundle stack in terms of the classical Ginson map of a vector bundle over a scheme. So to do that, let's go back to consider an affine scheme, and the same affine scheme we considered earlier. And if you pull back this vector bundle stack, so now let's try to understand the ginseng morphism of this vector bundle stack over the affine scheme U. So recall that on this affine scheme, the perfect obstruction theory is given by like a complex of a two-term complex of vector bundles, and the truncated cotangent complex is given by this, where this, recall that we have this close embedding to a non-singular scheme. And then this is, and just so now over this, this U is affine, that's very good, but this vector bundle stack is a stack. So to understand this vector bundle stack and objects on the vector bundle stack in terms of scheme, we take a smooth cover of this vector bundle stack by a scheme. In this case, it's easy. You just take, so recall that so first recall that we have just normal cone of U in W and normal sheaf of U in W, and they are embedded in the total space of E1U. This is just the dual. And then, so this will be a smooth cover of this, because this is the quotient of E1U by the action of the restriction of the tangent bundle. And actually we quotient out by this, we get this. Oh yeah, actually, let me do, so this pi is a smooth map from the scheme E1 sub U. Pi is a smooth of relative dimension D0, where D0 is the dimension of W, which is the rank of E0. And let D1 be the rank of E minus 1, and then so D0 minus D1, the virtual dimension D is D0 minus D1, and then it is negative the rank of this vector bundle stack. So now we have, let's see, so we have, so now we are on a scheme. So this is the flat pullback. So, and the pullback of this zero cycle is this D0 cycle. Oh, these two are just the same, right? So on this chart, on this affine chart, the virtual fundamental the virtual fundamental class on the scheme U defined by the perfect obstruction theory EU, which is the restriction of the perfect obstruction theory on X. This can also be defined in terms of this like classical, because now this is just the usual, now E1 is just a vector bundle over the scheme U, and you have the classical Ginsing morphism. So you apply this to the normal cone, the class of a normal cone, and yeah, because of this diagram is equal to this. Okay, so so apparently, so if okay, so this is the virtual fundamental class. So how about the virtual structure sheaf? Let's just describe it on this U. This is the virtual fundamental class. You see the intuition of this is like we take the total space of E1 and we intersect the normal cone of U in W with the zero section U. So now what we do with this, so this virtual structure sheaf determined by EU is we consider the structure sheaf of the zero section and the structure sheaf of the normal cone, and we take the derived tensor product over. Yeah, so this, so let's rewrite it in terms of this the stacky thing. Yeah, so it's in an object in the derived category on U. Yeah, I'm not sure if this is so, but in any case, this is what the virtual structure sheaf looks like on U, and globally, you get the virtual structure sheaf. So now to emphasize that this E is defined on OX. So let me write this. Yeah, so this is the, so this gives us the virtual structure sheaf on a virtually smooth Deligne-Mumford stack X together with a perfect obstruction theory. Okay, so now let's see actually if we have some smooth scheme, actually we recover the usual fundamental class and the usual structure sheaf. Okay, so yeah, let's first do the skin case. If you have a smooth skin, okay, then you see if you have a smooth skin, like for the open for the close embedding into something smooth, one can just take the identity map from U to U, and then the normal cone is just like, yeah, it's cone over U, but the fiber is just a point, so it's U, and now the cotangent complex, it's a smooth scheme, so it's just a cotangent bundle of U at degree 0. And then in this case, our perfect obstruction theory is like the same. So this is isomorphism. So if you take, yeah, so, oh, sorry, not, yeah, this is kind of trivial, but let's just check this. So you have, sorry, just this is equal to U, and then now we are going to form this cone stack. What you do is you just, this is just U, and yeah, you can think U is just a vector bundle of, yeah, so this is U is a vector bundle of rank 0, and then you mod out the action of the cotangent, the tangent bundle. Yeah, this is the, and but in this case, these two are identical, so these two are just the same. And then you can just do the intersection here. So this is just identity from smooth relative dimension D. This D is just the dimension of your U, and it's the rank of TU. So just apply this, but this is just in this case, this Insync map is just the identity. So we do get the fundamental class of U for a smooth skin. And similarly, if you have a smooth Deligne-Mumford stack, and you take E to be just the same as the cotangent complex, which is just the cotangent bundle. Then in this case, we also get the fundamental class, but now it's with a rational coefficient. And also similarly, because oh, actually I should, so how about, so for the virtual structure sheaf, you're just taking this. So you get the structure sheaf of U, and okay, yeah, so this okay, so okay, so the next thing is we should have this equivariant version, because like otherwise I think it's very important for this course that we have an equivariant version of this. So suppose that now we have, this is the Dillon-Mumford stack. Suppose we have the action of an algebraic group. Also, okay, so we need to be careful, like what is the meaning of a group action on a stack? So it's in the sense described in this paper. So suppose that you now have like group action, and now you're if you have a group action, then the cotangent complex, this will be object in the like derived category of G equivariant coherent sheaves. And also assume that we have some E, which is G equivariant perfect obstruction theory of let's say virtual dimension D. So then this construction will give us some equivariant class. And also when G is a torus, we have a torus localization of, oh yeah, actually maybe also virtual structure sheaf. So this is yeah, the main reference is Graeber Panda, but there are also other reference Baron, and also the original proof assumed there's a equivariant embedding of X into something smooth, and that assumption has been removed in a paper by Chang, Kam, and Lee. So in any case, let me just first write it. So you have I is inclusion from the G fixed substack in X, and on. So the perfect obstruction theory. So now G is a torus. So it has a fixed and moving part. So think it in terms of like dualizing this and think in terms of case theory. So the virtual tangent bundle, which is locally a difference of two vector bundles, when you restrict to the fixed locus, so torus acts on the fiber and you get the moving part, which is the we use the fixed part to define a perfect obstruction theory on the Dillon-Mumford stack, which is the fixed locus of G fixed locus of X. The moving part is defined to be the virtual normal bundle. Okay, so with this notation, this is in the G equivalent shell group, but tensor with so now G is a torus, k-dimensional torus. So Chell ring or cohomology ring is just a G equivalent. Oh, so by bullet, yeah, in the remainder of this talk, like bullet is a point. And so R is a polynomial ring of in k variables. These are universal first chain classes, and we work over rationals, and S is the fractional field of this ring. Okay, so this equivalent version is very useful for computation. So next important thing is we would like to have a relative version of this construction. So the setup is as follows. So now, again, we have oh, sorry. So suppose that we have so X is the Dillon-Mumford stack. So we have a projection. So usually, so in the following, we will have many projections. So projection from X to some M. So this M is a smooth arting stack of dimension M. And so yeah, actually M can be more general, but for the applications that we will describe today, this is sufficient. And we assume that this projection is virtually smooth of relative dimension D in the sense that there is a relative perfect obstruction theory. So relative perfect obstruction series EX relative to this smooth arting stack. So again, it's an object here. And now there is a morphism from this relative obstruction theory to the relative cotangent complex such that H0 is an isomorphism and H minus 1 phi is a surjection. So now we, again, to understand like this construction, we look at some affine charts. So we have an etalk, but now everything is like over M. So we have an etal map. So this is U is affine scheme. So we consider so I is a close embedding, and W is a non-singular scheme. Oh, so yeah, no, I want to say that let's see. So this is smooth of. So this is to a scheme. This is smooth of relative. Yeah. Oh, okay. So M is also smooth. Yeah. To a W will be a non-singular scheme, but this map from W to M is smooth of relative dimension, say D0. And now we can have relative intrinsic normal cone. So you take the same like normal cone of U in W, but instead of quotient by the restriction of the tangent bundle of W, we quotient by the relative tangent bundle. So then this has we have relative intrinsic normal sheaf. And again, we have close embedding of cone stacks over U. We take the so this is a vector bundle of rank minus D, where D is the virtual dimension. And here, this is a class of degree M, where M is the dimension of M. So this is in M plus d u. And so then, but now here, this intrinsic relative normal cone and relative normal sheaf, and also this curly E, they are globally defined on the Deligne-Mumford stack. So we have this, using the relative perfect obstruction theory, this construction gives a virtual fundamental class of this dimension, of this degree. So similarly, we also have virtual structure sheaf. Okay, so now let's apply this general construction to some examples. So the first application is, yeah, of course, Gromov-Witten theory. So let's now assume that X is a non-singular projective, or maybe it's also okay to do quasi. Yeah, so yeah, okay, so let me first assume it's like projective. So now we consider, so this is, yeah, I think this is like in physics, this is like we consider a two-dimensional sigma model, which means we consider maps from curves to this target. So let's first consider this x tilde. So take some curve class. We consider moduli of genus G, m-pointed degree, let's say effective curve class, pre-stable maps to X. So we can consider, so this is some category over the category of schemes. So what is the object when we restrict it to a point? So this is, so the object is a pair. So here is the domain is a genus G M pointed pre-stable curve. Yeah, it's just a nodal curve of arithmetic genus G, and the mark points are distinct and non-singular. So it's a pair, like this is the domain together with a map to X. Yeah, and we fix this curve class. And so this is a group point. All the morphisms are isomorphism if you have two pre-stable maps. So then isomorphism is the isomorphism of domain, the domain preserving the as a marker, curve with mark point, such that this diagram commutes. Okay, so now the so Rx in the Gromov-Witten theory will be the moduli space of stable maps. So this is a usually singular Artin stack, right? And then there's some stability condition. So the stability conditions, like we require the map to be stable. So if we assume X is projective, this is actually a proper Deligne-Mumford stack. But actually, this Artin stack is also already has this structure of relative perfect obstruction theory. So for fundamental class, we need to do this over the Deligne-Mumford stack. But the perfect obstruction theory is defined on the Artin stack of pre-stable maps. So let's now, since like by the construction, all we need to do now is to describe a perfect obstruction theory, then Baron-Fantaki's construction will give us the virtual fundamental class. So this is the moduli of domain, moduli of genus G M-pointed pre-stable curves. This is a smooth Artin stack of dimension 3G minus G plus N. This is virtually smooth. So what is the relative perfect obstruction theory? So over M we have, this is not the cone, this is just the universal curve. So we pull back the universal curve to get the universal curve on the total space, the universal curve on X tilde. So what is this X tilde? So the X tilde can be identified with some space of sections. You see, if we work over M is, it's like 2D sigma model coupled with gravity, but we can also fix a domain. So it's just a 2D sigma model. So so the fiber over this is just a morphism from C to X in class beta. And so over the universal curve, we have the universal map to X. So when we restrict to each fiber, this is just a map from C to X. Oh, sorry, I typo. And then the relative obstruction theory is the due of this. So if we consider So if we consider the dual of the perfect obstruction theory, restrict to this point. So we get so this is the deformation, infinitesimal deformation of map of a fixed domain. So this is when I is 0 and also this is a smooth arting stack. So this is actually a two-term complex. It has degree 0 and -1. So there's no obstruction to deforming the domain, but you have infinitesimal automorphism. Okay, so we see that the relative virtual dimension is given by the Riemann-Roch, and then we add the dimension of the moduli of pre-stable curves of genus G with MR point.
You consider it example, like very basic example.
Oh, very basic example when we want to say that in case U is smooth and you take the U is smooth, then the cotangent complex is just a cotangent bundle, and you take the perfect obstruction theory, which also so let me go back to the trivial okay, this U is this one.
Yes, he is U factor TU, like this E.
So it's a vector bundle stack, so which is the following. So you take U, which can be viewed as like rank 0 vector bundle over U, and TU is a rank D vector bundle over U, where D is the dimension of U. And there is a map from the TU to the 0 rank vector bundle, and you model it by, so fiber-wise, it's just the action of the tangent space on 0-dimensional on a point. That's it. So the base has dimension D, the fiber has dimension -D, so it's dimension 0.
And like this object, from which category is it? Like from category of stacks or from derived category?
So this E is something like geometric. It's a vector bundle stack over U.
And what is vector bundle stack actually? I'm like completely.
So vector bundle stack is we just in this you think like you have like so you have like let's see this is actually working. So suppose that you have so this is a vector bundle over U, and then because of this morphism, so there's this action by addition. So you can think the fiber of E0 acts on the fiber of E1, and you just quotient that. So view E.
So is it an object of derived category, like?
So now so this is the geometric one. So it's like the, how to say that? So we want to So in the okay. So in the derived category, you can think like locally free sheaves, but this is like the spec of theme. So this is a geometric. This is the total space of the E1 and E0 are total space of vector bundles. So E1 and E0 are scheme, and then we quotient by the action. So it's an arting stack, and this arting stack has a map to U. Is it that's all I can.
Okay, and also I was like completely.
Yeah, maybe it will help if I point out. Suppose if I have a smooth space and I look at like the usual thing. I take a drum complex of that stuff. So it's like the alternating sum of exterior powers. So this is also can be interpreted as like the Lie algebraic homology, like extracting an invariance for the action of the tangent bundle on the point. The two things are the same. So like functions on that quotient that's going to be the same as that's helpful.
Sorry.
So when we take functions on a functions on a quotient by a group, which is like the vector group, you can write some like Lie algebraic homology complex for that, and that complex here would be roughly like the cotangent complex of your variety.
And in this example, this factor is over like just action of abelian group of.
Yeah, exactly, the action for abelian group.
Yes, right. I think. And also, could you please show the Gromov-Witten slide?
Oh yes.
Like at the end, a bit below. Go to the bottom of this Gromov-Witten. Yes, here you've got x0 and x1 of some cotangent comma some unknown letter.
Which where is the line?
Like tangent bundle at the point M restricted to Xi, x0, and
So because it's a smooth arting stack, so the cotangent complex like it has two terms at 0 and +1, and if you dualize this, and you get degree 0 and -1. So the degree 0 term extension 1, this is the infinitesimal deformation of the domain curve. And you also have infinitesimal automorphism, which is extension 0. This is at a degree -1.
Yeah, my question was like this X is from cotangent from omega CD to what? What is?
Sorry, I think I apologize. I didn't define D right. Sorry, this is so here we are at this point, and I define D to be the. I define D to be the. Yeah, I apologize. I think that's what the confusion. Oh, sorry. So D is just the divisor of the mark points. So for example, if C is if C is smooth, right, then we get H0 C TC. So the infinitesimal automorphism is the space of vector fields vanishing at the mark points. And the extension 1 is this. Is this better?
So this this letter, which I don't know, was like just O of divisor of this mark points.
Oh yeah, sorry. I think yeah, this is because I didn't write clear enough, so that's why this is so this is as O. Yeah, a sheaf of OC.
Oh.
Yeah, sheaf of OC modules.
Ah, I see. Okay.
All right, more questions. Well, if there's no more question, let's thank Melissa for a wonderful presentation, and we'll see you and we'll meet again next week. Thank you, Melissa, so much.
Oh, thank you.